Unfortunately, it looks like I left my notes at home. But that's okay. It's not shouldn't be too big of an issue. So last time we started talking about state machines, right? And so I'm going to start off with reviewing these a little bit just to make re-hammer it home, right? So a state machine is essentially the fundamental building block for your project. Projects 1 and 2, you've been building up what we call the data path. For project 3, you'll be building the control logic for this. One way to do that is to implement it as a state machine. I haven't actually looked at the project 3 yet. We'll make sure we have to. I'd be shocked if we don't. State machines, anytime you start thinking about a state machine, any type of control logic, we want to start with a state machine diagram, because that will start telling us how to behave. What do we want out of the control logic? And it gets fairly easy to turn a state machine diagram into VHDL code. And so we're going to kind of walk through that. We'll first walk through how do we take a state machine diagram and turn it into a circuit, and then we'll talk how do we take a state machine diagram and turn it into code. So let's start off with building out a different state machine than we've had in the book. Well, let's say I want to build a state machine that detects a sequence. So let's say I want a circuit that will assert an output when it sees the sequence 101, right? This should be fairly simple. We start off with the state. We're just going to hang out there, and we don't do anything if we see a 0, right? That doesn't help us. If I see a 1, however, I'll call this state 0. I want to jump to the next state because now I've started detecting the sequence. If I get a 1 in this next state, in state 1, what do I do? Where do I go if I see a 1? So I got 1, 1. Where do I go? So you might think, oh, we got to start over. But we don't, because we're still here. We just saw a 1, right? So whether I saw a 1 this way or a 1 here, I've still got my 1. Does that make sense to everyone? So we don't want to start over, because if my sequence was this, 1, 1, 0, 1, and I wanted to detect 1, 0, 1, I did 1 back to this state, I would have to start, I'd just miss it. I'd be off by 1. So because I'd go 1, 1, 0, so I'd still be here, right? I don't want to be here, I want to be here. But if I see a 0, then we'll call this state 2. Now I'm looking for a 1. If I see a 0 at this point, I get 0, 0. Where do I go? In this case, we want to go back to the start if I get a 0. Because if I get a 1, 0, 0 here, I go 1, 0, I'm starting completely over because I don't have a partial of the sequence. So we got to be careful with that. However, if I get a 1, then I've got 1, 0, 1. Now you'll recall that there are 2 types of state machines, right? There is mealy and more. So a mealy state machine has outputs that depend upon the inputs. That's mealy. And then a more outputs that depend only upon the state that you're in. So let's start by making this a mealy state machine. So if I get a 1, 0, and now I get my 1, once again, I'm at a position where I could detect another 1, 0, 1, right? So if I get 1, 0, 1, 0, 1, I have here and here. It's my 1, 0, 1. So I want to detect that as well. So, and output our detection. So this is what we would call mealy. because the output now depends upon the input. If I want to change this to more, and if I want to be proper, right? If I want to make this a clear state machine for each of these, I would put a dash nothing, right? That's how I indicate that there's no outputs on all of these. And I would go through each of those and add it if I want to be fully proper. In general, unless I ask for it, it's not too big of a deal. Just only call it out when it matters. That being said, let's consider how we make this a more state machine, which is I don't get these conditional outputs. I have to make a new state. So this is how you can start to tell the difference between a mealy and a more state machine, is because, a little mnemonic, the more state machine in general takes more states to implement. Because I can't just do this. Now I have a state specifically to detect or to output that Z output that I've detected. And then I can go back to state one. Now, we have a little bit of an issue here. I'm clocking in data, and it is, so let's follow along. I get 1, 0, 1, and I've detected. But if my clock is at the same rate as the data that's coming in, now I'm in this state machine, I need to be careful that I don't miss the correct direction coming out of this. So I've gotten 1, 0, 1, and if I get a 1, I go here. And if I get a 0, I've gotten 1, 0, 1, 0. Does anyone see that? Because I want to detect this twice. So if I do 1, 0, 1 detected, 0, 1 detected again. So this is how I would recommend doing this, because I will probably ask a sequence detector question of you at some point, just because they're really common, they're really good state machines to think about, is follow it through. So after you've written the state machine, just start bouncing through with the pattern and make sure that you get what you want. And you can detect each of these, right? So I can go, well, what happens if I do 1, 1, 0, right? And I can step through and make sure that it all makes sense. And that's what's really nice about these state machine diagrams. This is simple one input condition state diagram. You could have multiple inputs, right? So you might have like a 0, 1, 1, 0, etc. We'll not jump to that quite yet. Actually, maybe we will, because I think this is a good spot to jump to that. So let's consider the stoplight. I used a simple one input example of a stoplight before, right? But let's build a multiple input for the stoplight. What are our potential inputs? So we know I'm going to find that the idle state is red. And we want to stay in red. So let's say that this particular stoplight uses a laser sensor to detect if a car is waiting at that direction, right? So we'll call laser. What other things might it have to consider? A timer. Yeah, we might just want a timer that we just rotate through regardless. It will then need, let's say, a pedestrian wants to cross, right? We don't just need to worry about cars, we have those pedestrian buttons. These are all things, we'll stop here with the things that might trigger us to go. What is something that might stop us from going? When wouldn't we want to leave red and go into green? If a cross light is green, right? We don't want to go green if the cross light is green. So we'll have a cross light, CL. So now we're going to start developing this state machine that says, well, we can write out each of these explicitly, or we can write just the conditions we care about. In the case of red, let's just write an expression, because this is pretty complicated for me to write here. But this is going to be I'll just call LTPC. Actually, let's make this X, right, for cross. So the condition to leave red, let's start with that one. And I go to green, is if I have,
first of all, not X, we do the overriding.
yeah, so we could do that. We could do not X and L or T or P, right? Similarly, we stay here if not that. So I'll just write,
It's basically if X.
well, if X or not
Any of those.
this is actually and, isn't
Yeah, it needs to be and.
it?
And it's none of those.
Yeah. Okay.
No, it should be.
Yeah, that's
if it's
not-
X or.
Yeah, well, we could just, the easy way of doing this, and then maybe use De Morgan's X and L or T or P not. Right, that's the easy way. Then we could De Morgan's this if we wanted to and get a different lineup, but I think we're okay.
What it should have been is X or, and then the ands of each individual not.
And of each individual not and not and not. Yes, that would make sense. Yeah, and that would be De Morgan's of this.
Yeah.
Okay, so now we've got our first transition out of green, and we have multiple conditions. Now, this is going to be, I'm just going to leave this essentially at a more state machine, and just say that my output is whatever my state name is, right? But we may have to deal with other outputs because we need to let the other light know that we're green. So not only do we have a green light, but we also have an X out, right? But what happens if the other one is green? Are we just going to sit and wait on its timer? Sure, we could. Or we could add an extra state that is like a waiting state. So I don't need that right now, I guess. There might be more interesting. Sorry, I'm puzzling through this one right now. So I could throw out this X and not worry about it. And I could go to like a hold state that says if L or T or P, let's go to hold and output our X. We're requesting that you change to red. And then we stay there until not X. In fact, I kind of like that one. So let's rewrite this one to say this is and this is and we'll call this request. And request outputs are X out. And it stays here, and I will rename this to X in. Stays here if X in is true. So I'm putting it R. Is X out a good one? Yes, this is fine. We'll reuse this variable. So I put X out and say, hey, I want to be busy. And so it's the other light is sitting and waiting for that signal, and it's going to transition back. Once I get not X in, I can come into green. While green, my XO is still true, right? And while yellow, my XO will still be true. Now my conditions for leaving green. And green just goes to yellow. Yellow is going to have an XO. We go here. Let's start with the leave condition. We leave green when our timer expires.
Or there's a request from the
X in request. And now we probably need to build up some logic to make sure that we have to
maybe like say a T-min or
yeah, sure. Good idea. T-min. X in and T-min.
and like our X's would have to be a little more complicated than simple binary because you need to have one for one for request.
So we actually don't, because I thought about that at the beginning. We don't really need that because we can use that same signal as request and R as long as this state knows that. So here I've treated X in as the is busy, and here I've treated it as requesting it to not be busy. But I can overload that operator just fine because they're never used for the same thing at the same time. So overloading that one is completely okay. If this were an exam and you created an extra variable for that, wouldn't be wrong. It would be fine. But we can reuse this one, and I think that's okay. All right, so then we're still outputting XO, and then yellow is literally just a timer, right? Timer. And we stay here, not timer. Green, then, we can again just say, we stay here as long as not T or X in, T min. Great, I think we're good. Now, how do we turn this into a circuit? Well, what we can do.
Wait, there's one thing I see. I mean, if neither of the sides, well, I guess there's a timer, but if neither of the sides has the request going, I can see, I guess the timer would take care of it.
The timer would take care of it.
They're read for a long time if they're, but it's.
Yeah, so there is actually a risk in here, is if we start these both up at the same time on the same clocks, then this red, they're both here. They both go, wait for the timer, they both jump to here. And both of them go, oh, look. Either they both go, oh, look, we're busy, or they both go, oh, look, we're not. right? It's a race condition because we don't know which one of them is going to receive or not. So they could either both jump or they could both get locked here forever.
So it might be best to set them with different timers.
Yeah, yeah, just the initial start. The right way to do this, and you'll see this, is they actually would put both lights on the same, inside the same state machine.
I was thinking that would be the way to go.
Yeah, that's the more intelligent way to do it. And that way you can, yeah, it's just better that way. This is okay for our purposes at the moment. I don't think we're going to run into any significant issue. Okay. So the next thing that we can do is we can build out a state table for this. Does this make sense to everyone? I want to take a moment and just make sure that everyone kind of followed building out a state diagram. Because now's the time to speak up if we didn't follow that. Okay, so the state table, if you recall, says we want to worry about what the current state is, what our next state is depending on the inputs, and what those outputs are. So, current state is going to be, well, I have 4 states, so 2 bits is just fine. So I'm going to have 0, 0, 0, 1, 1, 0, 1, 1. This state table makes it fairly obvious what good numberings is, right? Red, request, green, yellow. Red, rec, green, yellow. These are my numbered assignments. Now, my next state depends upon.
It might make sense to switch the green and yellow just so things are logically next to each other.
You kind of want that, except for the fact that the rule for creating the numbers for the states is if I'm progressing through, I want to increment.
Okay.
Yeah. If this one had the possibility of going back to request or something, then maybe we would want to reorder those. Because then you would want red and yellow to be adjacent because they both have the same potential destination.
Okay.
But they don't right now, so. Okay, so the next state, we're going to have, well, a lot of these, right? This one is where we start getting a little complicated because I have to deal with potentially all 4 inputs. And so this table is going to get messy really quick. But let's go through the process, at least for starters, and say, so red goes to either red or request. And this is if L or T or P. Right?
Not L or T or P.
Oh, right.
Itself.
Which would also be the one you recommended, which will actually be better, LTP knots. Right? And this one happens so normally what we would do is we would just write up all possible combinations of our inputs and then write what the next one is. What I'm doing here now is creating this kind of shorthand so that I can go ahead and look at the conditions that I'm interested in only, rather than having a 2 to 8, an 8 wide input table. Then request either stays on request or goes to the next one. And it's based strictly on X in and not X in. Then I'm going to pause here if everyone is following how I'm kind of doing this, right? So then the next thing I need to do is be able to turn these into a circuit, essentially. So we can make, this might get complicated. I'm kind of regretting having this many inputs.
I mean, you can take out maybe the pedestrians.
Yeah, let's take out pedestrians. Take out pedestrians, take out pedestrians. Now I only have 3 inputs. Now it is only 8 instead of 16 input variables. And I really wish this table wasn't directly in the way so that I could reach the whole whiteboard. Okay. Okay. And then up here we have Z, or what I call the output? Oh, X0. Exact. There we go. Now we have a proper table. And now we can fill these out one at a time. So next state is saying, based on these inputs, where do I go? Well, we know it's either red or request, and we do red if we have not L and not T, or request if we have L or T. So if I define these as L, T, and X in, right? I can start looking for anywhere that this L or T happens. So no, 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 there we go. And if I have L or T is true.
Last 2 as well. That's L, but the first,
Oh, this,
that one is the first one.
oh, yep, you're right. So then these ones are request. Right, those are our options. Lots of repetition. For request, then it's just dependent upon X in, which is the last one, where if X in is true, then we stay here.
It'll be every other.
And if green is 1, 0. For green, same kind of thing. This one we're looking at a more complicated instruction, but let's remove the T min just to keep this from ballooning. And we just have this timer or X in, and we're going to keep reusing the same timer, right? We're just going to reset it in each of these states and use it as the same input so that I don't have multiple timer inputs. Okay, so timer is, green has this, which is equal to T and, right? But I can also look at T or X in goes to yellow, which is 1, 1. So if I have T or X in, it's true. And we're going to, wait, did I skip one? Shoot, yeah, I skipped this. Request, green. Okay, I see what I did. T or X in, T and X in, T or X in, and we have those two. So we go to yellow, which is 1, 1. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then the other two just stay put. The last one only cares about T, which is the middle one. And if T is true, we go back to red. So T. And otherwise we stay put in yellow. And then X0 is going to be 1 when we're in any of these last 3 states. Boom. Okay, now we've built out this huge next state table. If I give this to you on an exam, it's only gonna have 2 inputs. I will not do A, this was terrible. This is why my notes are helpful, is because I forgot what state machine I was actually gonna be doing. So the notes that are sitting on a table at home where I'm languishing. Okay. So now we're gonna have a really unfortunately complicated circuit, so I won't walk through all of these. But let's say that we need to worry about, I need to make sure this ends up being okay and I don't have an issue. Yes, so yeah, I absolutely agree. So X out has a circuit that we can just kind of immediately jump to, right? That views the current states as its inputs, and that's all. So it just says, if current states are this or that, then we're okay. But this is why the 3 input was a bad idea, is because this OR gate that I make has to be so what the brute force way of doing this is saying, if I have any of these inputs, where it's so we would label this bit as CS0 and this bit as CS1. And so that I would say, if I have, well, what is it? CS0 and not CS1, or I have CS0 not and CS1, and right? Everyone see how that's making it? It's using just the current states to determine what they are. That gets pretty complicated. This can fortunately be simplified to just, and this would be X0, but we can take advantage of the fact that it's only that one. So I could just say, if I have not CS0 and not CS1, NAND, right? Boom, that is my output for X0 at all times. That's just combinational logic that watches what state we're in, makes a circuit. We may have to draw a K-map if we have a less trivial one, where you would draw, and we did this last time, right? So we can go back and watch that video if you need. Where you would have CS1, CS0, and what do we call it, X0. And then you could fill in the K-map for this. But the reason that this was such a simple one that we could just write the circuit, but this is the way you would do it if it wasn't super simple. Right, and this would output us some minimized combinational logic. So this one is just basically saying, If I have 0, 0 here, then this is zeros. Oh, x0 is unnecessary.
Yeah, you would have a simple,
I would just have a square.
yeah.
Yeah, because it doesn't depend on any other inputs.
Mhm.
But say it did depend on x in. Let's just pretend, right? Pretend it was a mealy output or something, then you would do that. If there was a third variable or I had 3 state variables, then I could fill this out. More state machines in general are easier to write this output combinational logic as well, because you don't ever have an input in the stat. It's only the states. So yeah, I'm glad you're understanding this because this would be really rough. Yeah.
When you're making the K-map, you don't pay attention to everything in between, just the space and maybe
In the Moore state machine,
in the map.
a Mealy state machine might be different. So, and I want to be very clear about something that's always driven me a little bit nuts about this. So I will talk very frequently, like Mealy and Moore state machines are completely different things. It turns out you can actually mix them. So it's more helpful sometimes to talk about Mealy and Moore outputs in mixed state machines. So right now, this is strictly Moore. But let's say that if let me think about the right way to phrase this. Sorry, I'm looking for a good example inside of this state machine. Let's say that we are entering, we're in green, and we're staying in green just based on t and x in. I could have a potential other output. So I go to this if it's t or x in. But let's say I want to differentiate between t or x in. They both go to the same place, right? But if it's a request, I want to know that, and I'm going to create a new output, and we'll just call it F. I now have a Mealy output in a Moore state machine, right? And now this one, the logic for F is going to depend upon an input and the state. So I'm going to, my K-map, when I try and make this logic, where the only time F is true is if my state, because we're going to this state, is on, I need to make sure this is right. So I'd be here, no, we want to use this state because it's going to hit that clock with this input. And then the next clock will be here. So we're going to have, if we're 1, 0, and x in is true. Right? That's my logic for F. And it's only going to be true for a brief little while. So the clock is going to hit while we're in here. We're going to look at the x in. We're going to have next state. And the next state we're going to be in this here. Right? And you may need to write even more complicated logic. I won't make you worry about this. If you wanted to have, depending whether you want this to stay true for the entire time that I'm in this state or not. Right? Because if I were to base this off of, so here, I could say if it's this and x in is true, then I could build it out and it would stay true because my AND gate is going to have this state, which we're going to be at for a whole clock cycle. Just something to be aware of.
Another question.
Yeah.
We are considering this as a Moore state. all the information in between is still useful to make a sort for each of the states, right?
Say that again.
We consider red, request, as sources on the HDL. All the information in between in the table can be useful to make the code for as well.
Oh, this code is you're asking if this code is useful for HDL? Yes, yeah, because these are indicating all of your inputs, and then these are creating states, which we'll get to today, how to make VHDL states. Yeah, pretty confident I can get that today. And so you'll see how we start building this out in VHDL. So this particular example, because I made it a more, is not particular interest for the combinational logic. So I will draw this up again. I wrote this up last time with a better example. Hopefully you guys had notes on that, where my current state is saved just inside of a DQ flip-flop. The output of the DQ we call current state. The input is next state. Current state loops back around into this combinational logic that we just started building. It takes these inputs, looking at current state and the inputs, to update next state. So, for example, you would have to build out all of the logic that says something like, so for my next state logic, I would have to have something that looks at if my current state is 0, 0, and my inputs are any of those, then next state is updated to true. So this one has to have 2 bits. The way we build the logic, and again, I covered this last time, so I won't go over the entirety of it because I want to move on to some new material rather than just review, is I look at the logic for CS1 and CS0 separately. So for CS0, how does it change based on these inputs? So I have L, T, and X in. I'll make sure I can do this correctly because otherwise I'm in trouble. Oh, I need more inputs than this. I'll jump back around. I will actually just make a video specifically rather than kind of drawing this out because I could figure it out, but it'll take me 10 minutes. I'll make a video for drawing up the next state logic. But for right now, just keep in mind, you can either think back to last time when I did this, or you can keep in mind that I draw the logic for CS0, CS1 separately. So it will have 2 blocks. So this would be CS0, and then I repeat this for CS1 with the same combination logic, and then combine those 2 for this current state. Yes. I will make a video because this is important and my brain's a little scattered at the moment. I've been not sleeping very well last couple of days. So let me find leave that up. I wish I had written it smaller, but what can I do? So in VHDL, when I want to use states, we have a tool that we can just create states. And it's called, we can create a new type. And we want to create a type, right? So we have like unsigned, signed, standard logic vectors, and so on. We want to create a type that just has names of our states. And the way we do that is what's called an enumerated state, where we say this type, and we make up the name. Let's call it states. Make sure I get the syntax right on this on the first try. Is let's do this. R rec green. So this is creating a type called states that has only these possible values. I can then create a signal, and both of these happen after architecture, before the architecture began. And remember, so when we have signal, we declare what the type is and what its name is. So let's call it signal current state is of type states, and I want it to initialize to, for simulation purposes, red. Then, state machines need a process. They always need a process. So we're going to start off with that process. And the reason we know that, why do we know it needs a process? Because it's sequential. Because the DQ flip-flops are clocked, we know it needs a process. Okay, and we're going to process on a clock and on a reset signal. In the case of a state machine, anytime you have sequential logic, I strongly recommend using a reset signal. And I'm a fan of, my syntax may get off a little bit, but you'll follow along. I prefer asynchronous resets. There may be calls that have synchronous resets, in which case it wouldn't be in the sensitivity list, but we'll start with asynchronous. So if reset is equal to 1, active high reset, then I'm just going to say current state goes to red. So if I reset it, it goes red. Else, if on rising edge of the clock, then this is probably where it gets new for you guys, but it's not too difficult. Case. Does anyone not know what a case statement is? Okay, so just one. I will walk through this, make sure you, that you can get it. And I will be very careful with my syntax. So I say case on whatever signal I'm interested in. In this case, current state. I want to make my decisions based on what my current state is, and then I have when sorry, since this is the first time seeing it, I'm being very careful with the syntax so that I don't botch it. Okay, So casing on CS, when I'm red, what I'm looking for. Now this is where I do things. I don't have an output signal. I just can say, well, let's say I do. Let's say I have a red LED. Then I would say red LED is 1, it's on. And if L is equal to 1 or T is equal to 1, then my current state needs to go to request. And then when request I need to turn back off the red LED. Right? Because, oh wait, that's not true. We're still red. We can leave red high, right? Because we're still waiting. We're not green yet. Then if xn is equal to 0, oh, not that equal, this equal, then current state updates to green. Right? And so on and so forth. Do you guys think you could write the whens for the following ones, right? So the next one being, when I go to green, I need to turn off the red light and turn on the green LED. Now, some of the practical sides of this is if I'm going to create a counter, right? So there are a couple different ways that I could do this. Is each time I enter a state, I could send a pulse that says, hey, reset this timer, and the timer would be its own process. Or I could create a timer within itself. Like if the whole thing is to wait for an amount of time. Shoot, what time is it? Oh, I got some time. That's good. Okay. I do want to talk about the timers, so we got some time. But does this make sense for the cases? Right. So let's go to, are we okay if I erase the state machine at this point? I'm a little bit hesitant to, maybe I'll erase just the top two since I've kind of written those out. Okay. So now we come into green. When green, then I do this. Well, I'm gonna leave on a timer. So let's create this timer inside of this case. And I'm gonna start by saying if timer is equal to 0, then, well, I've run out of time, so current state updates to yellow, right? Else, t is equal to t minus 1. So it's a countdown timer. I'm highly preferential to countdown timers. So what it's doing is, if it's 0, we go to the next state. Otherwise, let's just count down. Right? Outside of this, and the if, we just need green LED equal to 1. So And we probably need to turn off. Oh no, we're good. Yeah, we need to turn off red LED. Okay. There's an issue. What is the value of T? Well, I could, and this is the wrong way of doing it, but this is what people feel like they want to do. So they come in and they write, well, let's say that I have a 1 kilohertz clock and I want to stay green for 60 seconds. So then I need T equal to 60,000, right? And then they just write this here as their first thing. And then they go, okay, well, we come into the state, I make T equal to 60,000, and then I count down. Does anybody see why that doesn't work? Exactly. Every time a clock hits, it goes, okay, what is my current state? Oh, it's G. So the first thing I'll do is set T equal to 60,000, and then subtract 1 from it. The next clock hits. It goes, what state am I in? Oh, I'm in green. I'm gonna, oh, well, it was 60,000 minus 1, but now let's remake it to 60,000. Right, so that's gonna happen every time that we evaluate this state. So it's never going to get less than 59,999. So rather than putting it there, the right way to initialize timers in these states is in the previous state where you leave to go to that one. So if I say X1 and CS is green, then I initialize my timer here to 60,000. And now it goes, okay, timer is 60,000, we're green, let's start counting down. And it never undoes that countdown anymore. Everyone feel okay with that? Yep, so if you're counting, initialize the counter in the previous state.
Is that a signal?
Yeah, the T. Yes, this would be a signal of type integer. Because it's difficult to subtract 1 from standard logics. You can also make it as like unsigned if you'd want, because an unsigned can be subtracted from as well, I believe. But if you're not, I would just make it as an integer for my timers. Okay, do you feel good on cases? Yes, okay, good. Yeah, they're not too difficult, and they're extremely helpful. I don't think I need to write the remaining cases, right? And you can see how we don't have to worry too much about all of the complicated next state logic. So I'm still going to have you do that. I will probably like write an assignment. Like I said, I'll make a video. So you go through that, you understand what this is going to build for you. But VHDL, again, makes this so simple for us to build these state machines. One thing you need to be very careful about is we've talked a little about, and some of you run into this in the project, about dual driven. If you're trying to write to a signal in 2 different places, it will be a problem. So what you need to be careful of is if you're writing to a signal inside of the process, you can't write to that signal anywhere outside of the process. So like outside of the process, I can't write red LED is 0. Now it shares this if statement. So I could here in reset say red is 1, green is 0, and so on and so forth. But it's redundant. Because if I reset, I go to red, and then in red, I could just say red LED is on and the others are off. So it's good to set up whatever your idle state is with all of the signals as the condition you want them to be on. I've mentioned this several times, but for me, writing digital logic is sometimes about a process of discovery and just thinking through the logic of what's happening. So sometimes I'll get to yellow, move back to red, and realize that, oh, in my red, I need to go back and add that yellow LED is 0. Because it was on, now it's off. But I didn't realize that when I first wrote red, right? And this is fine and normal and encouraged to go back and think through your logic and make sure that you're accounting for all of the signals that you needed, right? The first time I write, I'm gonna have mistakes, but then I'm gonna loop back around and see what did I need. And then I might discover that, oh, but if I reset while I'm in the green state, I don't anywhere say that green is off. So now I need to address the green LED is 0, also in the red state. Now if I reset, regardless of where I reset, I'm okay. Except I'm not quite. What am I missing? X0. Right? Because if I'm not changing it inside of that state, it would just stay whatever it was. So I don't need to necessarily explicitly declare each state it is if it doesn't change. But I need to be careful that whatever my reset state is will get everything back to where I want it to be. And it's kind of a choice whether you want to do that inside the red state or inside of reset. Right, so inside of reset, you can also do that. But I like the idle state to make sure that it handles everything just in case something weird happens. So steps, create a new type that has all the states you might want to use, create a signal of that type, and then create a process using a case statement to build out your state machine. That's the steps for VHDL state machines. Be careful that you keep straight that states is the type name and the signal is what you use in the case, because that confuses a lot of people when they write states here. They'll try and case on states, but states is a type, not a signal. So be careful of that. Okay. We're basically out of time. We've got a little bit left, but we can call it here unless you have any questions on this. And I will, let me take a note real quick. So I'm going to post some homework today, and I'm going to post a video that covers next state logic. So you guys can learn how to build that. I talked about that last time, but I'll make sure there's a video so you can kind of rewatch it because it can get confusing. And I won't use 3 input variables because that made it a lot worse. If you run into issues reading through the book, because the book is decently well written, but for this chapter, it uses a whole lot of variable entered maps. And I'm staying away from those. So it's up to you if you want to kind of puzzle through the VEMs and follow along in the book away, or just take careful notes as we kind of follow through. If you're not following along the VEMs in the books and you're having issues with my lecture, make sure to send me an email with questions or set up office hours so that you don't kind of get lost and confused. In 3610, which you guys could take, I don't know if there's any prerequisites other than this class for 3610, actually, that maybe calculus, but I'm not sure. You could take that, not next semester, but a fall of next year, which I would recommend, kind of trying to take them close together. If you do that, we will launch into state machines really quickly. The very first thing that we build is a state machine-based VHDL program. All right, anyways, thanks for listening. Sorry I was a little scatterbrained today. Let me stop this recording so it can start converting.